And then you have to supply the fresh TM into your separators through that gas washers, if you remember.
Yes.
So there are 2 pumps in total, and we need to size these pumps.
2 pump in each. Yes.
Yeah. So now let us understand what is happening here. So we know the flow because we have calculated the flow of KOH solution. Right? First thing to get familiarized is hydraulic power equation. That is flow in meter cube per second into head into density of the material into G divided by 100. This will give you hydraulic power.
Hydraulic what?
Hydraulic power. We need to find the power
hydraulic power, yes.
for ultimately the motor of these pumps, right?
Yes.
First we find the hydraulic power, then we find the shaft power, and then finally we find the motor power. Okay?
Find the hydraulic power and shaft power and then the motor power.
Yeah. The hydraulic power equation is going to be flow.
No, what is hydraulic power in this case?
So you need to pump water, right?
Right. So how much capacity it can pump per second or per minute?
Yeah. So you need a certain amount of hydraulic power there. Otherwise, it won't flow, right? You need to create the pressure difference.
Right.
Because otherwise, there won't be flow because the pressure at.
No, yes, that's okay. That's the hydraulic power, and the shaft is.
Yeah. And this is the amount of hydraulic power we need to have. Then shaft power, not all whatever mechanical power we give goes into hydraulic power, right? So there is a certain efficiency. Now, since we are dealing with there are different types of pumps, right? Here it is a centrifugal pump. So shaft power is only 65% of. I mean, water is given in the shaft. Only 65% is given as the actual hydraulic power.
Right.
Okay. So again, the piston plunger pump also it's when shaft power you convert to hydraulic power, it is only 65% that is being converted. Okay.
Yeah, that's clear now.
Okay. Now in both the pumps, the equations are seen. You need to take flow in meter cube per second. What is the head? Now head I will come to later. Density you already know. Okay. And then G. G is gravitational constant. Divided by 1000. Okay. So this is the equation for hydraulic power. Our idea is to find the electrical power associated with these equipments because that is what we need to supply at the end of the day, right?
What is the third item you said?
Motor power.
QH kg per meter cube.
This one. This is density.
Density
of lye is 1290. Remember, 1200 we discussed. Yeah. I've written it here. So 1290 if alkaline, 1000 if PEM. Because in PEM we are using water, and in alkaline we are using KOH solution.
Right.
Are we clear?
Okay. The shaft is this 65% P motor.
Yeah.
How we calculated the P motor?
P motor is we take about 90% efficiency. Whatever you give here in motor, 90% gets converted to shaft power. Yeah.
90%, then it should be less. It's 0.9 to multiplied.
No, see, it is divided by. I need more power, right? In that case.
You are saying that shaft power will be 90%.
Yeah.
So motor power is more than yeah. Okay, 90% is the shaft power. Right, it goes down.
And we have given enough margins within these conversion factors. Okay, right. So that
the motor is more powered. The shaft is less.
Approximate power only, right? We are not going to detail design. If you go to detailed design, then you will get based on motors, RPM, how much flow will be there, all of that vendor will provide.
Right. Yeah, that's okay.
We don't need to go into that details because we are just concerned with the basic design. So we need to arrive at a number which is very close. If you actually go into pump sizing, right, then you will get a flow RPM curve. Then at what power, what flow will be there. All of that you will get. It will be like a pump characteristic. Based on that, you will buy. Preliminary calculation, this should be good enough. This is the fundamental, first principle based calculation.
Okay.
Yeah. So now, thing to consider here is your alkaline may be at about, see, we only need about a 3 bar pressure difference. Why do we need that only? I'll tell you. So if we go here, we don't need to create a huge pressure difference because all of the system is working at same pressure. So you create typically in alkaline systems, the pressure head the provided is about 25 meter. Okay. So 25 meter is nothing other than I will create a pressure difference of 2.5 kg per centimeter square. Okay. I will create a pressure difference of 2.5, approximately 2.5 bar. Why do you need that pressure difference? Because you need to push it into electrolyzer. In electrolyzer, you will have multiple, all of these concave convex structures that we talked about in our first classes. Then you need to get this back into a separator. So for that, you will need to have some pressure difference of about 2.5 to 3 bar. So here, if it is 27, output will be at 31.
Okay.
Okay, clear?
Yeah, clear.
So we need this is fixed. We need to create a pressure difference of about 3 kg. Okay. This is a standard thing that I have seen in the market also. Whenever we ask for this pump, electrolyte recirculation pump, generally the head is between 20 and 30. Okay.
Yeah.
So in this case, we are going to take 30 as a head. This is irrespective of the technology.
Okay. 30.
Okay. Now, density, we know, right?
Yeah, this is
Density of alpha. Yeah.
gravity,
So
we know.
just put in the equation Q into H into rho into G. Just understand that this Q is in meter cube per second.
Right.
Now, do the calculations, you will arrive at the motor power.
Yeah, this is okay. Same for this
Okay.
one.
Now, this one, first we need to estimate how much flow should be there. Okay. So now, 11.2 Nm cube is equal to 1 kg of hydrogen, right? Remember the conversions?
Yes, between one.
So 1 kg of hydrogen needs 9 kg of water. Because 9 kg of water breaks down, 1 kg of hydrogen is generated.
Yes.
Practically, so that means about for generating 11.2 Nm cube, you need about 9 liters of water. Theoretically.
Yes, that's right. To produce 1 kg of water or 11.2
when you typically go into a system, what happens is theory is not in practice, right? There will be practical losses in the system. So what we take is for every Nm cube of hydrogen required, you need about 1 liter of water per hour. That is the water consumed.
Okay.
That's my point. That is the water consumed, not the water flowing. That is the water consumed. You are breaking down water.
Right. So you mean the 1 kg water is used?
No. Yeah. 1 liter is 1 kg. Exactly.
So it's 9 kg water. So yeah.
Theoretically, 1 kg of hydrogen. If you need to make 1 kg of hydrogen, you need 9 kg of water. Theoretically.
That's right. Yes.
Yeah, that means 9 liter of water is required for 11.2 Nm cube. Theoretically. Practically, but when it comes to it is 1 Nm cube requires 1 liter or 1 kg of water.
Only.
Okay, so now if you have a
So
1000
just one thing, because we are saying 11.2 NMQ require 9 kg of water, okay, which will
yes,
eventually
yes,
be producing 1 kg of hydrogen. Now you are saying that
yes,
11.2 NMQ consume only 1 liter of water.
yeah. So this is the water consumed. It will be broken down into hydrogen and oxygen.
So where is the 9 kg water gone now? Because we are saying it is equivalent to 9 kg of water.
No, see, 1 liter water is 1 kg of water.
Sorry?
So 1 liter of water is 1 kg of water. Right?
Yes, that's okay.
Yeah. So see, 9 liter will produce 11.2 NMQ theoretically.
Yes,
I agree that.
that's right.
But practically, it is a one-to-one thing. There will be losses in the system, right? So 1 liter of water, if you give to the system, can generate up to 1 nm cube of hydrogen. This is 9
I
is to
didn't
11,
get
but
it.
this is theoretical.
Yeah,
But my
this
point is,
is
it is
9
it
is
will be
to
1 is to
11.
1.
And
Yeah,
now you are saying 1 is to 11. So
1 is to
why
1.
8? Why where 8 liter water is not needed? Why? This is a question from my side. Because we are saying 11.2 NMQ can be produced or equivalent to 9 liter of water to create
Yeah.
1 kg hydrogen.
No. First, let's understand. 11.2 nm cube hydrogen, if you need to generate, how much is that? 1
You
kg
need
of 1 kg of hydrogen.
hydrogen.
Right? This
Hydrogen,
we are
yes.
sure.
Or 9 liter of water. Needs
Now,
9 liter of
can we say this? H2O molecular weight is 18.
yeah, correct.
H2O breaks into H2. H2, H molecular weight is 1. H2 is 2 kg. Plus half O2.
Yeah.
If you balance it, it is half O2. O2 is 16.
Right.
So half of
60.
32 is 16. So
Right.
you break down 18 kg of water, you get 2 kg of hydrogen. This is theoretical.
Yes, theoretical, right.
Now, if you break down 9 kg of water, it will generate 1 kg of hydrogen. Right?
Practically, not practically,
Yeah,
theoretically.
theoretically. Yeah. So now
Yeah.
1 kg is equivalent to 11.2 NMQ.
1 kg.
1 kg is equal to 11.2 NMQ, right?
1 kg of hydrogen.
Is equal to 11.2 NMQ of hydrogen.
Okay,
Remember?
that's in the initial years also, yes.
So that means 9 kg of water will produce 11.2 NMQ.
That's right.
So can I safely say that 11.2 divided by 9 divided by 11.2 is the my water consumption per NMQ?
Yes.
Right? My point is, this is theoretical. Practically, it is 1-to-1. 9 by 11 is not 1, right? Getting my point?
Yes. So 8 liter water will
This is only,
still be out.
yeah, this is only 0.8 liter. Theoretically, you should be able to generate 1 NMQ with 0.8 liter of water.
Yes.
Got my point? Simple, straightforward. Let's write it. There should not be any confusion here. Let's write it. So 9 kg of water generates 1 kg of H2. Sure.
Yes.
In other words, we can call it 11.2 NMQ
NMQ. Yes.
H2. Right? This, in other words, can we call this 9 liter?
Yes.
So I can say that 9 liter of water gives 11.2 nm cube of H2.
Yeah.
So this means that approximately 1 liter of water is needed for every nm cube.
1 liter of water equal to 1 liter of nm cube. Or
Yeah,
1
it is
nm
not
cube.
exactly equal.
Yeah.
But
Yes, but
that
yeah,
is this is
approximately.
theoretical.
Point.
Yeah. What I'm saying
Yeah,
is that
1.2
practically this is the 1:1. So if I'm generating 1 nm cube hydrogen, 1 liter water will be consumed.
consumed. Yes.
Clear? Now, what we do typically do in sizing is, say you have a 500 nm cube electrolyzer. Okay.
Okay.
Okay. In other words, like 2.5 gigawatt electrolyzer. 2.5 megawatts, sorry. You know that, right? 1 nm cube is equivalent to, industry terms, it is 5 kilowatt. So 500 into
Yeah,
5 is 2.5 megawatt. Yeah.
I think
That is how we
you
arrived
said
at
so.
2.5. Typically, to generate 1 nm cube, you need about close to 5 kilowatt. When you talk in
5 kilowatt.
typical terms, you consider 1 nm cube is equal to 5 kilowatt.
Right.
Okay. So you have a 2.5 megawatt electrolyzer, generates 500 nm cube per hour hydrogen, and it consumes 500 liter per hour of water. Am I right or am I wrong? Yeah. Right?
Yeah, approximately. Yeah, it will be
So
more
I
than that, but
need
yeah.
to, this water is consumed, but I should keep everything stable, right? I should be adding this much water back to the system,
Okay.
right? Every hour, 500 liters is consumed.
Right.
That is gone. Now you need to add more water, right?
Yes.
So
500 liter
what you
per hour.
typically do, you assume that you are not only going to run it for 15 minutes. In that 15 minutes, you should be able to supply 500 LPH. So in that case, what will
Why
be the
15
flow?
minutes? Why 15
You don't
minutes?
want to run it continuously, right?
Oh, okay. Okay.
Your
Got
pump,
it.
you don't run continuously, right? Why do you run
Yeah.
it continuously?
15
It's a
minutes
piston flow.
out of.
Now there are few characteristics about this pump. I'll come to that. This is a high head pump because you need to take water at atmospheric pressure and you need to supply it at say 20 bar.
Okay.
Understand what I'm saying? Because water you are going to take from some tank, right? That water tank is normally not pressurized. So you need to take water from 0 bar to 20 bar. Otherwise, can you feed it into separator? All right.
Okay.
Are you getting my point?
Yes. Yes, I'm getting. So 500 liter water in 15 minutes.
No. Now 20 bar means 200 meter.
Didn't catch this point. We were talking about 500 liter.
200
Okay,
meter
200
means
liter.
that I need to generate a pressure difference of 20 bar.
Yes.
In watch and all, you get this 100 meter pressure rating, right? So what that actually means is you can go 10 meters underwater.
Right. Okay. Yeah.
10 bar. 10 bar is what that means. 100 meter rating.
It is more going into the mechanical and instrumentation part of the engineering. So getting
For
tough,
your
getting tough
understanding,
time.
just
Yes.
you can just simply go with the equation. We find the
Right.
hydraulic power, we get
QH.
the motor power. Yeah. So just understand that. I will tell you this. I think you will be able to picturize it also. See, the point is here everything is at same pressure. I need to create only 3 bar pressure to make the flow happen.
Yes.
But here the problem is this is at atmospheric pressure. And you need to supply to some very high pressure. Alkaline, I'll go. I'll come to later. Yeah. So in this case, you see this pump has to take from atmospheric pressure, and this is at 20 bar. You know that this is at 20 bar, right?
Right.
So you need to take from atmospheric pressure and supply it at 20 bar. And if your this side pressure is high than this side pressure, the flow won't happen. Right? The pressure generated here has to be higher than this, then only water will flow from this to this.
Right.
Otherwise, flow won't happen. So you need to generate enough pressure difference, which is in our case 20 bar. Because 0 to 20 bar. This is the 20 bar.
Right.
Now, in 20 bar, you don't keep 20 bar. You keep 21 or 22 bar. Because flow has to happen, right? If this is the 20 bar, this has to generate at least 22 bar.
Yeah, because some flow
has to
you will lose. Yes.
Yeah. Now, we know for a fact that we need to, our assumption is that we need to run it for 15 minutes and we should be giving 500 liter to the system. So our flow is, can I safely say that it is equal to 500 into 4. I need to supply 20 LPH for 15 minutes. If I supply 2000 LPH for 15 minutes, I'll get 500 liters, right? Hello, Aditya? I think you're on mute.
Yeah, I understand. I know. Yeah, I understand. For 15 minutes, if you need to supply, it is 1/4
I know the
so
flow
you need
now.
to multiply them.
I know the flow, and say I am taking, I need 22 bar at least because my system is at 20 bar. Then I'm going to specify 220 here. Okay. Then I'm going to, I know the density of water because this is going to be pure water, right? Nothing else. Then I know G as well.
Gravity remains same. Yes, for this one.
So hydraulic power will be Q into H into rho into G divided by 1000. Then from that we find the shaft power and then finally the motor power. All of these are correction factors. I mean, what we will find using equation is this, and then we'll have the correction factors based on the type of pump we are using. Are we clear?
Yes.
Okay,
Right. Yeah.
You have explained you how to calculate this flow. This flow you know how to calculate from the last class.
I will remember the formula, but having on the steps, yes.
I don't know. Next exercise that we do, right? We will be doing all of this together so that you are thorough. So this is the pump.
Right. So we know now about the pumps.
Yeah. So this flow estimation we have talked about. The heat management. There is one Excel that we studied, right? How to measure the live flow. Live flow. Yes. Once you have the live flow, you put that in here. You get the motor rating. Okay.
This is for pen. Now we see alkaline one. Yes.
Yeah. So idea being that now I will tell you what the big picture is. And now you will have something like this. Okay. I'm going to give you a picture of just try to understand what we are doing here. So you have say big MV going to come in, and then you're going to convert it to low voltage. I mean, not high voltage. Then you convert it to completely. You convert the MV, and then you convert it to low voltage. And then this is given to rectifier, which ultimately converts into DC. First thing is, I will tell you a system, and I will tell you the number of cells in my electrolyzer. You should be sizing the electrolyzer. What is the current? What is the voltage? I think you are able to do that. I think we studied that.
Yes, we studied in second chapter.
Yeah. So you will be doing that. And then you have 4 electrolyzers connected to one gas liquid treatment.
To the one gas liquid.
Gas liquid treatment. So that means this is a 1000 into 4. 4000 NMQ gas liquid treatment system. For that, you need to find the electrolyte flow.
This is, can you remove your cursor, please?
Yeah.
For ATM MQ.
Yeah.
MQ per hour.
In this case, we will find out how much cooling water should flow. Everything we know how to calculate. Right? Let's see that also.
Okay.
How
This
much
exercise we need to do.
Instrument air calculation, don't worry about it. Discuss into this. And then purification unit chilled water. So we will estimate how much chilled water is good. Yeah, Aditya.
So just trying to read this the amount.
Yeah. So the exercise will be for you to design a system. I will tell you a configuration. You will have to design a system wherein you will size the electrolyzer, you will do the gas liquid treatment, you will size the pumps within it, you will calculate the cooling water flow required, you will size the purification unit, you find the size of the heaters, and then you find out the chilled water flow. So it will be like a complete exercise, basic engineering exercise for you.
And heater we also. Okay, fine. And we will be showing this in the next class.
Yeah, we will be completing the purification also today. Okay. Purification is simple. Don't worry about purification. I will just do purification unit.
Okay.
Now in purification unit, I think you remember the steps, right? There are multiple
So
steps.
can you write also the problem statement? What needs to be calculated? Electrolyzer sizing. I know the pumps. You also
No, I
said
will
the
come to
heaters.
that. I will do an exercise with you. Okay, for this. This I am just showing you. This is an entire module.
Module. Okay. Okay. I thought maybe you are giving me this so that I design the electrolyzer size, which you already
No. I will do a design for you completely. Then I will give you 2 exercises.
So we will do this together, and then
we'll do this
we will.
Then second one you will do, and then I will get it.
Okay. Yeah, I thought maybe I will do it because the electrolyzer sizing and all we already checked. Okay. Anyway.
In this case, you will be not only sizing the electrolyzers, you will be sizing what are the equipments under it also. What is the other equipments? And their power also. So you will be getting the complete clarity. Okay. So now we go into purification. So I think you remember in purification, first we have to heat it up.
Yes.
The oxo reactor, you cannot supply it at 80 degrees Celsius. I mean, you cannot supply it at 40 degrees Celsius. So from 40, you are going to take it to 80.
Right.
Remember?
Yeah, remember in last class we did.
So I am going to take it from 40 to 80. So the delta is 40. Heater power required is this much. Again, heater is just like a cooler, right? In a way. I am not cooling, I am supplying energy. But the equation still remains the same. One place we are taking away heat, one place we are giving heat. But the equation remains the same. Right? I need to increase the temperature of hydrogen by 40 degrees Celsius. The goal remains the same. You know the CP? CP is the energy required per kg to increase it by 1 degree Celsius, if you don't remember.
Yeah.
So once you know the amount of hydrogen that is flowing into the system and the regeneration flow, I will come to later. and you will be able to, we just find out the kg value. So we converted NMQ into kg and then put a 10% factor there.
Right.
Additional 10% factor, and then you know the CP and you do the delta T.
Right.
Just multiply, you will be able to get how much heater rating should be. And you will degrade it because you never size heater according to what you need. You are going to degrade it by at least 15%.
50% more capacity.
Yeah. This is purely electrical energy to heat energy. There will be some losses also. So in degrading, it will be taken care of.
15%.
So you learn how to size the deoxo heater. Can I safely say that?
Yes.
Yeah. So this is the first step. So this is the first step. Here I have to heat it, then supply it to the use. I don't have the heater here. I have the heater here. So 40 degrees Celsius you have to increase. I think you understood that, right?
Yes.
Do I need to demonstrate down there? No. Okay.
No, that's okay. Yes.
Okay.
Only
So
this calculation
now,
I need to check again for
it is the simple equation. So two equations that you need to study in the whole course is one is heat supply, that is MCP delta T. And then the other one is the pump equation. QH rho G divided by 1000. Two equations.
M we know, CP we know, delta we know.
Based on what is the required item, you know the CP. You can just put it on the internet anywhere. It is there. Just check if the units are correct.
Right.
Okay.
What is this 49 hydrogen?
40.
40 is the
Sorry.
delta, yes. On the right hand
I
side.
didn't get it.
49.
This one. This is what you're talking about.
No, white. On the white sheet. On the next to it. On the next column.
Yeah, this one.
The hydrogen 49. The third one. Please come down CP, hydrogen 49.
This is CP. I don't know what is that. I am. That's a different thing. I'll come to that.
Okay.
This is a different calculation. I'll come to that. So now I already told you that this is an exothermic reaction. If you remember
So
our conversation.
heater power is calculated how? MCP delta, right?
MCP delta T. So we are increasing the temperature of hydrogen by 40 degrees Celsius. So
Right.
that is
So
the heater power.
MCP delta, yes, that's the heating power, and then we degrade it to 85. Then it's a rate.
Now it goes into the reaction chamber, or where pellets are present, palladium pellets. I told you that is a catalyst. Now in catalyst, reaction will happen. Thing about this reaction is that it releases energy. So that means you are going to go up from 80 to some other temperature.
Down.
Got me?
I mean, the down temperature, it releases the energy.
Yeah. So now, see, it is going to release energy. Anything that releases energy heats up its environment, right? Anything that takes in energy, it will cool down its environment. Thermodynamics. See, if you simple, you've seen hydrogen balloons, right?
Yes.
Have you seen hydrogen balloons? So if you put some kind of some lighter near it and light it up, it will blast right immediately. Why does it blast? With fire. Because it is releasing energy to the atmosphere, right?
Yeah.
A blast is nothing but a release of energy to the atmosphere.
So cooling
there
down.
Are certain
when the energy,
when
energy
there are
is
certain
released,
reactions where
it's cooling down.
Yeah, when you release, it is going to heat up. If it is an endothermic reaction, it is going to cool down the environment.
Okay.
So if delta G is, I mean, you can think about it like this: in exothermic reaction, energy is given to the system. You can think of it like a bomb blast. It is a chemical reaction that causes immediate release of energy, so that will heat up the environment. If energy is absorbed to make the reaction happen, then it is an endothermic reaction. So this is an exothermic reaction, and when every mole of oxygen is 1 mole of oxygen reacts, it will produce about 576 kilojoules of energy. Are we clear?
Yes,
One mole of oxygen reacts. Let's go into that. Let's try to understand what that is. 1 mole of oxygen reacts, it will produce 576 kilojoules of energy. So this energy directly goes into heating the system.
which system?
Our system.
Heating.
We have the gas which
heating
is now at 80 degrees Celsius, right? Yes. Okay. You heat the item. You are heating it to 80 degrees Celsius because your reaction will start at 80 degrees Celsius.
Right.
Then you
That's clear.
send to your palladium catalyst. The reaction will start. The thing about this reaction is it will release energy. So when you release energy, the system's temperature is going to increase. So your 80 degrees Celsius hydrogen temperature is going to increase.
Right.
Got my point? And every mole of hydrogen will generate about 576 kilojoules. Clear?
Yes.
And we know the percentage of O2 in H2, right? We said it was somewhere around 0.5.
Yeah, half of that. 2 molecular H2 equal.
So now that is about 20 nm cube, right? 0.5 percentage volume by volume. If my total nm cube is 4,000, I say that 0.5 percentage if it is oxygen, then I know how much oxygen is present.
Uh,
4,000 into 0.5 percentage. It's 20.
yes.
Right. I'm telling that my total volume is 4,000. Okay. I'm telling that my
Total volume
0.5 total volume gas
of
flow.
hydrogen is 4,000.
No, total volume of the stream is about 4,000. And I have about 0.5 percentage impurity. Okay.
Steam meaning the hydrogen plus water, meaning the water
Not
molecule.
water, oxygen. First is oxygen. Then you convert oxygen to water vapor. Okay. That is what you are doing. I mean, just remember what we have discussed. Okay. So this is about 95 to 99.8. But rest of it is बाकी जो है ऑक्सीजन ही है ना? पहले हम रिएक्ट करवाएंगे, उसके बाद क्या हो जाएगा? ऑक्सीजन खत्म हो जाएगा, बट वाटर वेपर होगा. So we are still here, not out of this. We are still in deoxidation. Are we clear?
Yes.
Sure है ना? You understood, or should I explain anything?
Yeah, I understood. It's a 99.99% of hydrogen and 0.5% of oxygen. Yes. So
Now I
4,000.
know the total flow. I am taking total flow. So that means I have about 20 nm cube of oxygen present.
Yes, in this 4,000 units.
And you can remember this factor. 1 nm cube has about 44.64 moles of oxygen. Okay. Clear?
Yes. So 892 more.
Yeah. This is standard. You can put it anywhere, you'll get it. 1 nm cube is
Right.
standard, some standard of hydrogen. Okay. Like I said, nm cube is used when it is a standardized flow, not a volumetric flow. So then you will get this. This is a constant, and you know how much moles of oxygen is present, and from that how much energy is generated, you can find out. This is the moles into energy. Energy is kilojoule per mole, but I have to convert it in terms of kilowatt hour. So I am dividing it by 3600. Unit conversion.
You are dividing by
3600. I am converting kilojoule to kilowatt.
right.
Kilojoule per second is kilowatt.
Right.
And this much.
But we are discussing the kilowatt hour. So kilojoule per second is kilowatt hour.
Yeah, see, kilojoule per second is kilowatt. Kilowatt hour. I will tell you what we are missing here. This is the flow in an hour. Normal cubic meter per hour.
Yeah.
So I am going to get 20 nm cube of hydrogen in an hour, not in an instant.
Right.
So in an hour, I will be generating this much of energy.
Right. Okay.
Just this is simply moles into kilojoule per mole. I know the moles. I know how much energy will be generated in a mole. I just multiply. I get kilojoule value. Now I need to convert kilojoule to kilowatt hour. Okay. See, you can do it anyway. Just that all the units has to be aligned. You can do it in
that's okay. I understand. Just it's a conversion.
Yeah.
Because the field is different. I have never done it because mostly it's a power side.
You will get
that's
the
why it
chance
is.
to do it. I will share this one, and then you will be doing it also. So then you will get it. Get the hang of it. It's basically the constants. Remember the constants.
Right.
I have put the constants in. Top level you just need to change, but you need to understand what you're doing also.
Right.
You're finding how much oxygen is there in the impurity. And once you know the oxygen, per unit oxygen, how much energy is going to release, you find out. You multiply both, you get the total energy. Now that total energy goes into increasing temperature of the system. This is the Q. Can I say this is the Q now?
Right.
I am supplying 142 kilowatt hour of energy to hydrogen, 4000 nm cube of hydrogen, which is at 80 degrees Celsius already. Okay. So all I need to find out is what is the delta T that is going to be there. Because I know Cp, I know mass, I know Q also. Q is how much? This much.
Yes.
Right? I just find it out by 80 plus. Because delta T is this one. Right?
That's okay. Yes.
Yeah. Q by M into Cp. E13 divided by C5 into E5. Q by M into Cp. That will give me delta T.
Right. And Q
I
is
should know
your
the
142.848.
Yeah. Q is my that one. Now I got the delta T. This is the only unknown here. So I got the delta T. But the point is that is delta T only. I should have the starting temperature, which is 80 degrees Celsius.
Right.
Understood the concept?
Yeah, that's okay. How much it came as a result?
Yeah. No. I am supplying 142.84
No,
megawatt hour. to
142.848 kilowatt hour. Yes, at the 80 degrees. So now the temperature
again.
will become 223.
Yeah, so it is going to be 80 plus delta. But you need to understand this because 80 is the starting temperature.
No, that's okay. I understood. We are starting with 80. That's why
Yeah.
the
So
the
now
original
this
temperature
temperature
was
is at
80.
171.
Yes.
So
And
80
then you
was
need
the,
to add 80.
yeah. And there is a concept of regeneration flow, if you remember, in our dryers. Do you remember that?
Yes. Generation.
You remember the stream?
Yeah. 2 pumps are needed.
Yeah. So that is what the regeneration stream is.
Yes.
Here, what are we
Is
doing?
used and then
We are taking 10% of the stream, heating it from 27 degrees Celsius to 300 degrees Celsius. Be clear?
yes.
We need one heater in dryer, right? If you remember, in every dryer.
Yeah, this I remember.
Size.
Purifications.
Yeah.
Yes.
So the temperature is, I only take 10% of the stream. If my size of the plant is, size of the particular purification unit is 4000 nm, I take only 400 nm. Yeah. And that I have to raise the temperature from 27 degrees Celsius to 300 degrees Celsius. I know the delta T, I know the Cp, I know the M. So I will get Q.
Thank you.
Right? Are you getting me?
Yes, yes, that's okay.
Yeah.
So
So I know
171
that.
plus 8. Yeah, just one minute. 171 plus 80. It is not that this direct calculation.
This one. Yeah.
No, the temperature of gas at outlet is 171. And
Yeah.
the temperature was already 80 degrees.
Yeah. From 80, I need to have a delta. So 80 is this, okay? 80 is the starting temperature. Delta we are finding out. 80 plus delta will be my current temperature, right? Are you understanding there?
Not really, because up to the temperature, yes, energy generated, yes, I got it.
No, no.
And
What
temperature,
will
if
happen?
you remove your,
Think about it like this. I need
can
a
you remove your
0.0.
cursor from 142? No, can you remove the cursor? And just
Yeah, I
click
can
somewhere
find
else.
out the delta T. I can only find out the temperature difference. But the
No,
actual
you are
temperature is,
highlighting. You are highlighting it. Just remove your highlighter. Yeah. Click anywhere else. Yes. No, because it is showing me 80 plus E33. I am not able to see the absolute value.
no, C. That is Q. See, we know Q, we know M, we know Cp. The only unknown is delta T.
Yeah, that's clear. Yeah.
Now,
So
we need
now
the
Q
actual
divided
temperature.
by M. Yes, Q divided by M and Cp.
Yeah, that will give me
That's
delta
okay.
T.
Yes.
My actual
The
temperature
delta
is
T. 80.
that plus 80. Yeah,
Yes.
clear, right?
Yeah. Can you remove your cursor? Can you click yes? Now it is 171. This is what I
Yes.
was saying. 171 is the final result, right? So if the gas is at 80, so 171 plus 80.
No, it is already accounted. That is what I was showing you.
So how we reach 223 delta?
No. 223 we are not reaching. No. Let's wait. This is purification.
Okay.
Purification
No,
is
this I
over now.
understood.
No,
171 I understood.
after purification, you remember the purification system? We cool it down after that immediately.
Yes.
This is a dryer. If you remember dryers, it goes into generation. This is a different concept. Now it is only water vapor. It is cooled down after the oxidizer. It goes into dryers. dryer, one will be in generation, one will be in regeneration, and one will be in half generation. Whichever there is a bypass line taken to regenerate the dryer. So we are going to find out the heater for this dryer. You remember this how the 3-dryer TSA works?
Yeah, a little bit. Yes, I remember that. When it's saturated,
Yeah.
then we are using it. Yes.
I think the disconnect is because the class is happening at such an interval, right? And the disconnect is coming. I mean, the class is happening at a very huge interval, right? I mean, 2 weeks of no connects, then this things come up.
One more reason is that now the mind is saturated from the morning until now. So it's very hard to, first of all, this is not a subject which I studied, at least for me. The conversion of the at least the units, it takes me some focus. And until now, the
My thing
battery is
is right.
almost gone.
I can actually slow it down. I'm just concerned about the code standard. If you are fine with it, I will go slow. Because I think you had a request where you told me that to complete it. That is why I was picking up the pace.
No, that's okay because I think it is also going a bit slow than expected. I was expecting the in August or September first week to be over. But yeah, one class at least apart from Saturday is necessary. Yeah. Okay.
So the thing is, we are completely sending this to the regeneration tower where moisture will get absorbed and downstream it will go. Okay, this is pure hydrogen. From that, you are going to take a 10%. Why are you taking the 10%? Because one dryer will be saturated by that. Right. We need to regenerate that dryer. How do you regenerate that? By sending a gas at very high temperature. Yeah. Why do you send the gas at very high temperature? Because it can take away moisture. Are we clear? Yes. So now 10% will be going into regeneration tower, heated from 27 degrees Celsius to 300 degrees Celsius. This goes here, this comes out, takes out moisture with it, and then goes into a cooler. Again gets cooled down to 27 degrees Celsius. Some of the moisture will be left in this cooler, and then it goes into half generation tower, which will take the remaining moisture from it and then merge it with the main stream.
This we read in the previous question system.
Yeah. I think you remember now, right?
Yes.
Okay. Not getting you saturated now. This is kind of how it looks. I think we showed this diagram also in the class. So now, only thing we know for sure is we need to heat it up from 10% stream from 27 degrees Celsius to 300 degrees Celsius. Can we agree on that?
Yes.
That heat is rising we are going to do. So M we know. How do we know M?
Already we know 39.285. The upper one, the volume.
10% regeneration flow we are fixing, right? So now we know it is 400 Nm. 400 divided by 11.2. It's going to be 39 kg. We know M, we know Cp, we know delta T. Right? In this case, I'm only increasing the temperature from 27 to 250. That means delta T is 223. Right?
Why 250?
See, you need to take it to very high temperature. This is again an inherent characteristic of your desiccant.
Right, as per the purification process, yes. We take it to high, but it is written 250 to 300.
Yeah, 250 to 300 degrees Celsius.
Yes.
I've taken
so anything between 250 to 300.
Yeah, it will typically depend on the system, but we are keeping some temperature that the PC is feasible. Okay.
Right.
250. we are fixing because we need to have a preliminary spacing of things. Right? We need to
Yeah,
go with
that's
certain
a kind of
assumptions.
constant. Yeah. Okay, that's kind of.
Yeah.
And 27
Now,
is coming
27
from
is
this
the
half.
if you remember after purification unit, the gas is coming in at 27 degrees Celsius after deoxidation.
Right.
Remember, we have this gas coming in at 170 degrees Celsius. Then you have a cooler which cools it down to 27 degrees Celsius.
Right.
And then only it goes into dryers, right? Comes here. These are 27 degrees Celsius. Here, no heating or cooling, so it is out at 27 degrees Celsius. Then it comes back in. This is when it is going from 27 to 300 degrees. Are we clear? You can think of it like after this starts.
Yeah, the point is that I do remember all this, but this absolute value like 27, 100% stream, 250 to 300, this I didn't, remember by heart during this study.
No. You don't need to remember by heart also. You just put it in Excel, keep it. Just remember that it is somewhere between 250 and 300. Why do you need that
Right.
temperature? Because if you need to regenerate a desiccant, you need that temperature. See, silica, you can heat up and make it leave moisture. If you know,
Right.
it will go from
Right.
pink to black to blue again. If you heat it. Same thing we have. It is kind of like silica, but a different material, which is better suited for the purpose. Again, fundamentals remain the same. If you heat it up, it will leave out moisture. Okay. Yeah. So now we know the deoxo heater size. We are going to take it up from 27 to 250. Now we can estimate the size. We know M, we know Cp, we know delta T. So we know the heater power.
Right. And then we know the degree.
Yeah, we take a correction factor. This is the calculated one. We typically keep 85%. I will reread it by 85%. So I will need more than that value. I take 40 kilowatt. Okay.
Yes.
Clear, right?
Yes.
So we have sized both the heaters for your purification unit. And this heater will be three heaters of 3 heaters will be there, right? This is not only one heater. Every dryer will have its own heater. So you have 3 heaters of this type and 1 heater of this type. You understand? Or should I explain? Go to that image.
No, it's okay. I will surely revise it. It's not
No. See, it's
going
simple.
100%.
Every dryer will go through 3 modes. If you remember me telling. So every dryer will go from generation to half generation and then to regeneration. So every dryer is equipped with a heater and a cooler. We are only showing one here because we need to show 3 modes.
Yes. So dryer and heater, this is 2, right?
This is 3 dryer. I have shown you 2 dryer system also. And that it is going to be like this. This is a 3 dryer system. There is no loss. Okay, Aditya.
Okay. Yes.
So each dryer, think about like this, each dryer will have its own heater and cooler because it needs to go into regeneration.
Yes. That's right.
Yeah.
Heater and cooler will be there.
So I need to, if I'm ordering some heaters, I will need to order 4 heaters. 3 for dryers and 1 for deoxidizer. 3 of them will be of the same size, 1 will be of a different size because it is for a different purpose. Clear?
Clear.
Now we go into hydrogen cooling.
I think we rest
You know,
here. We
yeah, I think I can stop here. But the thing is, it is again MCP delta T only. We are using cooling water just to cool it down. We are finding how much chilled water we need.
okay.
Same equation, MCP delta T. We are just finding out how, in the last case, we found out cooling water, right? Here we are using chilled water. Okay, we will take that up in the next class.
So now we are reaching to what? We are reaching to the alkaline, or we are reaching to the same system? So sorry,
I didn't get you.
just 1 minute.
This is like a system design. So purification is same for both alkaline and PEM.
Yeah. Okay.
Okay.
Yes.
In BOS, we have studied how to size the pumps of each of the equipments in both alkaline and PEM. What differs? The design philosophy is the same, just that the fluid flowing will be different.
Good.
You remember?
Right.
So now, basically, what we have done is this is the complete picture. We have done electrolyzer sizing. We have done the electrolyte flow sizing. We have done the pump sizing. We have done the cooling water flow sizing also. Now, in this purification unit, you can find out the deoxo heater sizing and triad heater size. Now, the only thing remaining here is chilled water.
Yeah.
How much chilled water is required for cooling here in purification? Okay. See, we need all of these values. Okay. You're going step by step, understanding what is what, and then calculating. Okay.